Okay, hi. This is the stuff that we covered last Wednesday in class. So this is the temperature coefficient, determining the maximum and minimum number of modules that you would put in series for a series string inverter. Here's the equation right here. VOC times bracket 100% plus parenthesis temperature minimum minus temperature standard test condition times temperature coefficient VOC. So we're going to get the VOC from the data sheet. The data sheet is for a specific module, so we need to know, be able to identify what is the VOC, VMP, ISC, IMP, the temperature coefficient VOC, temperature coefficient VMP, I'm sorry, not VMP, PMP, power max power. So we get the VOC and temperature coefficient VOC from the data sheet. Temperature minimum is the record cold temperature for that location that we're building a system for. Temperature standard test conditions is 25 degrees C, and that is a constant. So let's add the numbers. So I picked out a module. The module said the VOC is 45 volts times 100% plus parentheses negative 28 degrees C. So this is record cold for this location minus 25 degrees C times temperature coefficient of negative 0.31% per degree C. So the first thing we're going to do is figure out and calculate what the temperature differential is. Negative 28 degrees C minus 25 degrees C equals negative 53 degrees C. Just enter this into your calculator as it's printed. You'll get negative 53 degrees C. Next step, once we have this, is to multiply by temperature coefficient. Here's this laid out in the next parentheses. Negative 53 degrees C times negative 0.31% per degree C. Enter that into your calculator just as is printed, and you'll get 16.4%. So we're going to gain 16.4% voltage of that module because of the cold. As cold, as the temperature goes down, voltage goes up. Next, we're going to change these percents into decimals. Move the decimal place over 2 to the left, and you get 1 plus 0.164, which equals 1.164. Multiply that by your VOC, 45 volts, you get 52.38 volts. So this module won't put out 45 volts in negative 28 degrees C. It will actually put out 52.38 volts. So we can't go over our voltage rating for our inverter or in application. If you remember, residential is 600 volts, so we can't go over that 600 volts. So here's that 600 volts residential maximum divided by our new VOC, 52.38, and we get 11.45 modules. So we can't do 11.5 modules, so we round down. 11 modules would fit under 600 volts. 12 modules would be over our 600 volt minimum. Now for calculating minimum number of modules in series, we have roughly the same formula, but we're adding in T add, or temperature add. T max is the average high temperature for that same location, and that's ambient temperature. So ambient temperature is different from cell temperature. So we have to add a application temperature to boost that up to actual closer to cell temperature. So if it's a rooftop mounted application, I'm going to add 30 degrees C. If it's ground mount, I'm going to add 25 degrees C. If it's a pole mount, I'm going to add 20 degrees C. VMP is I get off the data sheet. We still have the 100% plus. Now inside the temperature parentheses, I have T adder, T max, which is the average high temperature ambient. Still have temperature STC, which is 25 degrees C, times temperature coefficient power max power. All right, for that same module that we've been working on, the voltage max power in this case is 36.8 volts. Brackets times bracket, 100% plus bracket parenthesis 30 degrees C adder, 41 degrees C ambient average high, minus 25 degrees C standard test conditions times negative 0.41% per degree C. So this is our new formula. We plugged in the numbers. First we do temperature. 30 plus 41 is 71. Minus 25 equals 46 degrees C. Next, we're going to multiply by our temperature coefficient power max power. 46 degrees C times negative 0.41% per degree C. And as a result, we get negative 18.86%. So we're losing almost 19% of our voltage on the average hot day. So we need to get above that minimum voltage to we still are in that efficient sweet spot of the inverter. And it's possible that we don't have enough voltage to even sustain the operations of the inverter during these hot times. Okay, so next up I'm going to add this to this. We're going to take and add 1.0 plus sign is missing, negative 0.1886, and we get 0.8114 as a result of that. Next up, we're going to multiply that by the VMP, and we get 29.86 volts. So on a average hot day, our module is going to be putting out 36.8 volts. It's going to be putting out 29.86 volts. Now, to determine the minimum number of modules, we're going to have to look at the inverter data sheet. In the inverter data sheet, it will tell you what is the maximum power point voltage operating window. So for the Fronius inverter, I believe I handed out that cut sheet or that data sheet for the Fronius inverter in a previous class. Nonetheless, the MPP voltage window for the Fronius inverter is 200 to 480 volts DC. So this is the sweet spot. That's where the inverter wants to operate at and operate at its most efficient. So 200 is our minimum voltage. So I'm going to take 200 divided by 29.86 volts equals 6.6 modules. We can't use 6 modules. That'd be too low of a voltage, so we have to round up in this case to 7 modules. So as a result, we can have series strings as big as 11 modules and as small as 7 modules. So somewhere in between there, 7 and 11 is the best matchup of series strings in parallel for this particular inverter. So what are the voltages we're looking at? Max volt at 11 modules would be 11 times 52.38 equals 576.18 volts. The minimum voltage, 7 modules times 29.86 volts VMP equals 209.02 volts. So this configuration would work fine for that particular inverter. Even though this is greater than 480 volts, that 576 volts would be seen at sunup on the record cold day. And as that sun came up, it'll start heating up the modules, lowering that voltage down. And then eventually it'll, when the inverter engages, then it'll be in VMP. So this would work just fine. So for the quiz, expect to see roof fill calculations. I'm going to give you a module and a roof size. You're going to tell me how many modules, what's the weight, what's the size, all that stuff. And then a temperature coefficient calculation. And then being able to identify different components, electrical characteristics off of a data sheet, like what is the VOC, what is the VMP, what is the IMP, what is the ISC, what is the temperature coefficients, what is the weights, things like this. All right, so this should get you down the road and on the way. We'll see you next Wednesday.